Good morning, everyone. I think it's time to start this webinar and would like to welcome you all to yet another EHPA webinar on case studies and real-world applications of large-scale heat pumps in the industry. Let me shortly introduce myself. My name is Sonia Bianconi. I'm EU Projects Officer at the European Heat Pump Association, and I would like to I will be moderating this webinar today. This webinar is held within the Spirit project. If you can pass to the next slide, Irene. And I will be talking about this project very briefly in a few minutes. Let's go over the agenda very quickly. We will have an opening statement by Benjamin Zulstorf from DTI. And then our four panelists will present various technologies and implementations of high-temperature heat pumps in the industry. We will have Christoph Fleischmann from Spilling Technology, John Van Rohen from GEA Heating and Refrigeration Technologies, Sander Gehlen from Gehlen Counterflow, and Vincent Grass from Nestlé. Before starting introducing the Spirit project, if Irani, you could go to the next slide. I would like to give you some housekeeping rules. So as you can see, you cannot activate your cameras and mics. You, however, are free to and actually encouraged to write your questions in the chat. Just please make sure that you add the name of the speaker you're addressing these questions to. And also note that this webinar is recorded, and the recording of the webinar together with the PDF of the slides will be made available right after this event. So next slide, please, Irene. As I was mentioning, this is a webinar that is being held under the Spirit project. Spirit is the acronym that stands for Implementation of Sustainable Heat Uptake Technologies for Industry. It is a project funded under the Horizon Europe program. It kicked off in September last year, and here you can see a wonderful picture of the consortium at the kickoff meeting in the beach of Petten in northern Netherlands. It has a duration of 3.5 years. And it counts partners from 17 partners from 8 countries all around Europe. Next slide, please. Here you can see the partners that are involved in the project. We've got 5 knowledge providers. The coordinator is among them. TNO indeed is the coordinator. We've got 4 technology suppliers, 3 end users, 2 communication and dissemination partners, and 2 partners that are doing the business support. Next slide, please. Spirit aims at fostering the uptake and the development of high-temperature heat pumps in the industry. And here you can see the demonstration sites that will be implemented within the project. We have the first demonstration site that is within the Stella Polaris plant. Stella Polaris is a prawn processing plant located in northern Norway. And then we have the second demo site that is Tiense Suiker, which is a sugar factory located not far away from Brussels, so here in Belgium. And finally, Smurfit Kappa, whose plant is located in Czech Republic. And in the slide, you can also see the capacities reached and the temperatures reached by the heat pumps that will be installed in each of them. And yeah, the temperatures reached go from 143 degrees to 157. But let's not take more of your time. Yes, please, Irene, if you can switch. Yes, I would like to invite you all to follow Spirit Online to know more information about the project. And also, if you feel like it, you can sign up for the biannual newsletter. Next issue is in September, and so if you want to keep updated with the project, feel free to just follow us on our social media and website. But without taking too much of your time again, I would like to give the floor now to Benjamin Zuldorf. So if you can switch the slide. So Benjamin is a center project manager at the Danish Technological Institute. He is an internationally recognized expert in the field of heat pumps for industry and district heating, and he's responsible for the research and development activities at the Center for Refrigeration at Heat Pump Technology at the Danish Technological Institute. In addition, Benjamin is also the coordinator of Annex 58 about high temperature heat pumps as part of the technology collaboration program on heat pumping technologies within the IEA, a program that has participants from 14 countries. So without further ado, please, Benjamin, the floor is yours. We can
super.
Not hear you. Oh, yes. Yes.
Now you probably could hear me. So thank you very much for the introduction. Very nice to see you, see so many here. So good morning also from my side. As you said, my name is Benjamin. I'm working for DTI, and I have one slide on let's say what we're doing for industries. Irene, if we go one further. We're working generally with heat pumps, but for industries, I tried to capture our services in one slide. So we are working with a technology development where we are developing components, compressors, heat exchangers, but also entire systems. We are testing those, and we can actually test it at full scale in megawatt scale for high temperature heat pumps. In fact, we have the inauguration later today in the afternoon, so we're very soon looking forward to that. And we're working with integration at end users, where we are consulting end users in how to, let's say, apply new technologies and how to decarbonize their process heating. And obviously, high temperature heat pumps are playing a large role in this. And with this background, we are involved in a variety of projects, technology development projects, as we have it here. For example, with Spirit, but also other projects. And one of those is Annex 58. Which we have briefly introduced, Sonia. So if we go to the next slide, I will explain a bit why we look at high temperature heat pumps in general. And after all, I think most of you have probably seen this slide before. But when looking at the process heating, or in general, the total energy demand in industries, we can first of all see that process heating is accounting for a large chunk of the total energy demand. And we can also see that there's some high temperature heat requirements above 500 degrees and so on. This is really heavy industries, but there's also quite a considerable share required at temperatures, let's say below 250 degrees and below 200 degrees. And this is very well in reach of heat pumps. Not as we have seen it a few years ago, but there have been a lot of developments, and we know that heat pumps can reach these temperatures well above 100 degrees. And we also know that heat pumps have the best, let's say, socioeconomic performance, the best life cycle performance. And we know that this would be the preferred technology for a variety of applications, not all applications, but really a broad variety of applications. So with this knowledge, if we look on the next slide, we could see that plenty of studies have actually been conducted looking at from this technical potential, so how much heat is in reach of high temperature heat pumps, to what should actually be covered if we consider investment costs, operating hours, electricity prices, other fuel prices, and so on. And one of these studies has been done by the IEA. It had been published in May 21. It's a net zero by 2050 roadmap. And probably some of you even have seen these figures as well. So if we look at the diagram in the top graph, where I have the red dashed line around, we can see what technologies should be implemented to reach net zero by 2050. And the light purple one, this is fossil fuel boilers in the very top rows. That's by 2020. It's actually up to 400 degrees, what they call low temperature heat demand. And we can see the light purple ones, that's fossil fuel. Then we have the green ones, biomass. The light blue ones, that's electric heaters. And the yellow ones is other heat sources. And then when we see, what has to happen until 2030, then we can see fossil fuel heaters are being phased out from industry. And it is mainly replaced by heat pumps, but also some electric boilers here. And this trend is continuing towards 2050. But the point here is, it's huge numbers. It's 15% should be covered by heat pumps, up to 240, up to 400 degrees until 2030. And this simply means if we consider, It's global figures, right? It's up to 400 degrees. It's global figures where we say, okay, there are also a lot of countries which are not so far in the development. This means developed countries must go first, and first, I mean, front runners must go first, right? And if we now conclude from these numbers, then we can simply see that plenty of applications here in Europe have to be covered by heat pumps, and many of those are high temperature heat pumps. And all this should happen and be implemented by 2030. And knowing that a lot of heat occurs maybe between 100 and 200 degrees, where heat pumps are not that, let's say, major now. I will come back to this, what it means. And it is a considerable effort right now, and it is a huge challenge to bring these technologies into application. And this is why I'm so happy about this webinar today, because you will see some great examples of where this actually has been realized, and where there are some good products being implemented and under further developments here. So if we go to the next slide, then I try to visualize a bit what we need to actually exploit this potential. And of course, first of all, people have to be aware of the technology, and they have to be committed to sustainability and decarbonization. They have to know the technology. They have to know how to use the technology. They have to know where not to use the technology. They have to know the characteristics and so on. And they actually also have to know, okay, how can we exploit these technologies? And this really requires a variety of stakeholders. And then, of course, we would like to go to market deployment, but in between, obviously, I said it, we need some technology developments here. That's both on component and system development. We need to test and demonstrate these technologies. It has to be really a variety of technologies for all these plenty of applications we see out there. And then, okay, we develop technologies, that's obvious. And if there are any end users around, and now think, okay, we just wait until heat pumps are ready, and then we implement them. Then I can tell you also have a task, and this is to become ready for heat pump implementation. This is something which takes several years, and you can start already doing this today and prepare your processes for it. It is typically to adopt this technology. There will be some early movers here and early majorities, and this is really what we're addressing here right now. Start with retrofitting the industries towards heat pump-based process heat supply, and develop the decarbonization strategies. This is what we do when we're out at end users and consult them. It is actually absolutely crucial to have a long-term strategy to avoid, let's say, wrong investments and making the decisions correctly to avoid technology lock-in, so to say. And of course, boundary conditions are also a crucial factor here. So the ratio of what we're paying for electricity and the ratio to alternative fuels like combustion fuels are becoming more beneficial for heat pumps. So and this simply allows that we can also operate heat pumps at higher temperatures. Regulatory frameworks are becoming more beneficial for electrification and energy efficiencies. There are subsidies, incentives, and some market developments. And then, of course, we will see some market deployment where we see the heat pumps being deployed in the market. It will be implemented in commercial projects. There will be a learning curve for operators and suppliers, and we really need to build up a massive supply chain for these large volumes of heat pumps. So let's go to the next slide. I will give some background where we on how we see, let's say, the world, based on the results we have from Annex 58. And Annex 58 is this, let's say, a project as part of the IEA, International Energy Agency, which focuses on coordinating, communicating the knowledge about a technology. And this is about high temperature heat pumps with supply temperatures above 100 degrees. We from DTI, we facilitated it. I'm the operating agent for it, and we have 14 countries joining. We have 5 tasks in it. First one is a technology overview. I will present this one here today. We have developed concepts for integration concepts for processes. We develop guidelines for mastering the transition towards it. This is an application work package. And we're talking a bit about, let's say, specifications for heat pumps, how to define them and how to test them. And obviously dissemination, that's what we're doing today. So we are spreading the word about this technology. You can note that actually from next week, we will enter the last 6 months, and there will be plenty of results. So stay tuned for the reports coming out during the next month. If we go to the next slide, Then we can see an example of what we did in the technology review. So we have collected 2-page descriptions, very handy descriptions of possible technologies. When we started the annex, there was more or less the common perception that heat pumps, they work until 90 degrees because we had this ammonia system then. But we said, okay, there are actually technologies in development, and when looking ahead, it's very important to look ahead and also consider technologies which are on the way. Some of them are major for market, and some are on the way. And we mapped them, we collected these technology descriptions, and we managed to gather actually 34 technology descriptions in total. It includes all the most relevant information, and they are available on the homepage where you've seen the link before. It includes everything from performance data, capacities, maximum temperatures, working fluids, and so on. Also actually specific investment costs, technology readiness level, and size and footprint, and so on. So we collected these, and on the next slide, we have tried to analyze it a bit. First of all, we can see different, or the state of the art of high temperature heat pumps is strongly dependent actually on the compressors. And for this understanding, there are different kind of compressors being used. There are compressors, let's call it from process industries. This is very often integrally geared turbo compressors. It's quite advanced technologies. It's application-specific design, and they have a relatively high initial investment cost, and this economy of scale we are looking into here. So these make mostly sense for capacities above, let's say, 15 to 20 megawatts. Maybe 10 megawatts or so, but really they're really economically competitive at these very high capacities. And then we have these compressors which come from, originally from refrigeration, so commercial compressor or commercial refrigeration, industrial refrigeration, and this is in the several hundred of kilowatts or megawatt scale, and we can typically apply them up to 15, 20 megawatts or so. So these are the main groups which we see, and keep that in mind when we're looking at the results. So if we go to the next slide here, then we can see an overview of all the companies who have provided technology descriptions, and you can see very well-known companies. You can see very new companies, kind of startups, first movers, and so on. So that's very diverse what we can see here. And if we go to the next slide, then we can actually see. We asked them to provide a picture of the technology, and already by this picture, you can see also kind of the state of the art where they are. Some have provided a sketch of the functioning principles, some have provided a 3D model, some have provided a picture of their pilot plant, and some have provided pictures of realized installations. So there you can get a grasp of how far they are in their development already. I have one more slide on, I think, on the analysis here. So here we see maximum supply temperature and what they have indicated on their own over the capacity. And there's, let's say, a group of technologies up to 160 degrees or so, which is being developed for minor or for smaller capacities in the megawatt range. And this is typically the refrigeration compressors, upgraded refrigeration compressors. And then there are these very advanced compressors from process technologies, which are very, very advanced and can reach higher temperatures. But please do not conclude that this means that we can reach high temperatures at plenty of capacities. This means that actually we also included technologies at a lower tier A. And it has to be considered, or when making a judgment of how far we are with the state of the art, then it is important that some of these technologies are at a different technology readiness level. Some of them are at a technology readiness level as low as 4. Some of them are already market mature. The cost is a factor here. Some of them are quite expensive at the moment. Some of them are more cost competitive, and we have a factor of 6, 7, 8 between the cheapest and the most expensive technologies. Efficiencies are largely different. Sizes, footprints are very different. Geographical availability is different. It's also different if we are talking about technologies which can be scaled and supplied and have a service maintenance network, and so, or if it is really let's say a startup with a new kind of technology. So keep this in mind when looking at these figures, but at least it gives an indication that quite many developments are ongoing here. So if we go to the next slide, then we also did the same for demonstration activities. And I won't go through too much in detail. But briefly explaining, we have the 2-page descriptions, because we also wanted to communicate some demonstration activities which have been realized to have these good examples being communicated. So they are also available on the homepage, and we managed to gather 16 descriptions here. and they also include most of the key performance data. And what we have seen here is really demonstrations from different industries, food industries, chemical industries, and pulp and paper industries. So have a look at it. It's interesting reading. So let's go to one more slide, because then I can explain that this fits very well with our developments, what we are involved in on our own here from DDI. We're currently working on, actually, I'm showing here 6 large-scale projects where we're going for demonstration of high-temperature heat pumps. So these are 6 of our high-temperature heat pump projects where we're having large-scale demonstration in a megawatt or 500 kilowatt scale. The smallest one is 500 kilowatts, and the largest one is 4 megawatts. So we can see here, for example, the steam compressors we're working on. That's a combined system of turbo compressors, 2 turbo compressors directly driven, and a spindle compressor. So turbo compressors in a 2-stage arrangement can lift around 50 Kelvin. The spindle compressor has a higher temperature lift, and actually the spindle compressors, right now down here in our laboratory, and we are testing it for, let's say, proof of concept, and then we'll upscale to higher capacities. We go for full-scale testing by the end of 23, and hope for on-site demonstrations 24. The hydrocarbon system is also part of the superheat project here. It's a 2-stage or cascade system, butane up to 120 degrees, isopentane up to 160 degrees. We are testing it actually here. It's in our laboratory here today, and we are soon starting it up. And then we're building also a CO2 system, also at 500 kilowatts. This will be also tested here by the end of the year. We're currently in the detailed design, ordered first components. So we will also have the full-scale testing here. And then if we go to the next slide, there's just 3 more examples. First 2 are from a Danish project, also with some international partners. It's different compressors. It's a screw compressors, 120 degrees, 160 degrees, also with hydrocarbons, isobutane, isopentane. It's fast coil compressors in this case, and this will be integrated in a drying process. Can also supply this 120 to 160 degrees. And then there's another one. Actually, it's the same temperature ranges, up to 120, 160 degrees. It's SRM compressors, a bit larger capacities, and it's steam compression here. And then finally, this is a pentane system, which we are developing as part of the Spirit project. It's together with GEA screw compressors. It will be providing steam at 140, 145 degrees. And this is a 4 megawatt installation for sugar production in Belgium on one compressor. And we're going for full-scale demonstration in 24 directly on site. So this was an overview of what we do, and this fits very well with the overall picture as we see it. And if you go on, I have one last slide on to conclude here, and we tried to summarize all this in let's say one in one figure, and that's quite comprehensive. But going through these temperatures and the capacities, so as you can see, there is an upper stage. This is 200 kilowatts to 10 megawatts. And then up to 120 degrees, there we can actually see prototypes had been available some time ago. Full-scale demonstrators are being demonstrated right now, and we can see various technologies becoming commercially available 24, 25. There are some first movers, obviously, but the bulk of technologies will become available during the next years. And then we can see it will be established as a preferred technologies after this. Up to 120, 160, we can see a slight delay here, but also here we see prototypes being available. Actually, at the moment, we can see that full-scale demonstrators are being demonstrated in the projects you have seen before. We can see that various technologies will become commercially available 25, end of 25, 26, and we will also expect a larger uptake in the market here during 27. Going to above 160 degrees, we can also see some first prototypes here. This is even a bit more delayed. This is ongoing work. Full-scale demonstrators, we expected by the end of 24, maybe to mid of 26, and then afterwards commercialization. If we go to the large-scale systems for what are called from process industries, here we could actually see, and that's quite exciting, we could see that these technologies were first commercially offered because they trusted, they had the technologies available in other applications. So they trusted the technologies, and they basically had the technology transfer, so they could offer it commercially. first demonstrations. I mean, this is heavy investment in these scales. It's a bit dependent on end users and the boundary conditions, but we expect it up to 120 degrees. We could see it here actually, and then we can see a larger market uptake afterwards. And for above 120 degrees, I mean, we've seen temperatures being claimed up to 280 degrees. So this will obviously start with the lower temperatures, but we also see here that it is being offered commercially. And when we see first demonstrations, again, it will probably be, I don't know, 25, 26. If they're ordered now, there will be some time for development and uptake. But this is currently as we see the overall picture, and I think this fits also quite well with the coming presentations. So I know Sonja's getting nervous. I have just one slide to let you know, if you are interested in high temperature heat pumps, make sure to sign up for the high temperature heat pump symposium. We have had it now 3 times before. It will be 4th time in Copenhagen, 23rd, 24th of January. And we're expecting around 300 participants here, plenty of presentations. It's a 2-day event. So make sure to check it out and sign up for the newsletter to stay up to date. So yes, I think that was a presentation from my side. So thank you very much for the attention.
Thank you, Benjamin, for this very insightful overview on the state of the art of high temperature heat pumps. Well, as you said, the aim of this event is indeed to dive into different applications of large scale heat pumps in the industry, and we are going to hear this with our next speakers, how we're going to hear a bit about from the manufacturers, the technology manufacturers, but also from the end users that decided to install a high temperature heat pumps in their plant to power the industrial processes. And the first panelist of this discussion is Christoph Leschmann. Christoph is sales engineer at Spilling Technology. He studied chemical engineering in Dortmund, Germany, and he's been working at Spilling for 18 years. Spilling, as you might have seen in the first slide, is also part of the Spirit project involved in demonstration site 3, if I'm not mistaken. So please, Christoph, the floor is yours.
Thank you very much, Sonja. Yes. In my presentation today, I would like to introduce the Spilling steam compressors, the piston compressors from us, and the possibilities of combining them with other heat pump systems to supply process steam for the industry. The next slide, please. Here in this slide, you see the idea of heat pump integration in industrial processes. The upper picture shows the situation, how it is at many processes today. A fossil-fired boiler is supplying high-pressure steam process heat to a process, and the most heat is afterwards going from the process into the atmosphere. So it's completely wasted, and the idea now of integrating heat pumps is shown in the lower picture, that as much waste heat as possible from the process is recovered and lifted from the lower temperature level where it's normally available, again to a higher temperature level with a heat pump to supply it again in the quality like the process heat is required. And now these heat pumps, industrial heat pumps, which are in the market or which are coming up, they can be characterized according to the temperature level where they are operating on, like Benjamin's slide also has shown. And in the next slide, I would go a little more into these different temperature ranges as we see it. From our point of view, here is a cascade of different technologies shown in their temperature characteristic. Temperature characteristic from the source side, what is going into a heat pump, and the sink side, what is coming out of the heat pump. At the lower end, you see these ammonia heat pumps, which are, say, state-of-the-art, and which can use low temperature heat with, say, 20 to 40 degrees Celsius, and lift this heat to higher temperatures like 80 up to 90 degrees Celsius maybe. Heat sources here on this lower temperature range might be, for example, cooling water also exhaust heat from chillers, from refrigeration machines, for example, or also heat from the surrounding, say, landscape could be used, like, for example, river water could be used as such low temperature heat, or also geothermal heat, for example. Okay, therefore the ammonia heat pumps are existing. In the middle temperature range, what is shown here in this slide, you see high temperature heat pumps, like they are now coming up, new innovative units, which are able to lift exhaust heat or heat from 60-80 degrees Celsius level on their source side to above 100 degrees Celsius, up to 160 degrees Celsius. And some of these new high temperature heat pump systems have in their in their program also steam producing part on the sink side, so that they can supply with these machines or with these systems low pressure steam with, say, 2 to 5 bar. The other way, what can be done to bring 60-80 degrees Celsius heat to above 100 degrees Celsius can be the way like shown below in the middle, with a series of blowers. Therefore, first water steam in the vacuum is produced, say with 0.2 bar absolute or so, and then with say 5, 6, 7 blowers or turbofans, one behind each other, this vacuum steam is compressed to overpressure level, also to 2 to 5 bar, something like this. And from this low pressure steam level, 2, 3, 4, 5 bar on, now, for example, piston compressors like from Spilling or other mechanical vapor recompressor units can compress then the steam to higher pressure levels, like it's required for industrial processes, up to 10 bar, 15 bar, 20 bar, even to 40 bar, like shown here. Okay, this complete cascade, like it's shown here, was not often realized, or honestly speaking, I don't know installation where this complete cascade from starting from 20-40 degrees Celsius as source side and on the sink side high pressure steam was so far realized. But we have some feasibility or some projects which are in the feasibility study phase. One project, for example, where river water shall be used as heat source in the US, and on the sink side, 6 bar steam shall be supplied for a district heating system. Another example is where the cooling water as heat source at a chemical plant in France shall be used. It has about 27 to 35 degrees Celsius, and again 10 bar steam shall finally be produced from that, also in this 3-stage combination. And another project, what I think is now close of realization, is installation in Austria, where the exhaust heat from chillers shall be compressed upwards to finally also 12 bar steam pressure level in a pharmaceutical plant. The applications where heat sources with 60-80 degrees Celsius are available, and only the high temperature heat pump or the blower constellation has to be combined with spilling steam compressors or with other mechanical vapor recompressors. These are more often found. So there are a lot of projects now in the feasibility stage or even in a more detailed engineering stage. Next slide, please. Now I would like to go a little more into the technology of these piston steam compressors. You see here a 6-cylinder unit. We built these machines with 1 to 6 cylinders. The number of cylinders is depending on the steam flow rate, which shall be realized with them, but also to the compression ratio, which shall be realized because we can combine these cylinders to up to 3 stages in one machine. So a 3-stage compressor could look like this, that at the inlet, at the first 3 cylinders, for example, we have 2 bar being compressed to 6 bar steam. Then the steam is going to the next 2 cylinders where it's compressed then from 6 to 15 bar. In the last high pressure cylinder, it's then compressed from 15 to 25 bar. And this all in one machine. And by this, the saturated steam temperature can be increased for more than 100 kelvins. What we should have with these piston machines on the inlet side is that the steam entering into the unit is in a certain way pre-compressed. So we say there should be at least around 2 bar absolute, 1 bar gauge. Otherwise, the mass flow, what we can handle with these units, is comparatively low when the steam pressure is even lower at the inlet. And so the machines also become relatively expensive. So it's an economical point of view that there should be these 2 bar at the inlet about. On the outlet side, like I've mentioned in the slide before, we reach with our standard units up to 40 bar. This corresponds to about 250 degrees Celsius saturated steam temperature. The typical mass flows through these machines is 2-3 tons per hour up to 15 tons per hour. In some cases, we can also reach 20 or even 30 tons per hour. Now, the advantages of such piston machines is simply their good efficiency, not only at the full load operation, but also in part load operation. So these machines are also very flexible. We can throttle them down to 30% flow rate. And in the complete regulation range between 30 and 100% flow rate through the machine, they have always the same efficiency. And so also the electrical power consumption is really proportional to the steam flow rate, meaning when you have 50% flow rate, the machine also consumes only about 50% electrical power. On the next slide, again, these efficiencies are shown. On the left, below, the yellow curve shows the COP as function of the compression ratio. For example, when we compress steam with a factor 3, for example, from 4 bar to 12 bar, so when we triple the pressure, we get a COP of about 6, meaning that the thermal output, which is coming out of the compressor, is 6 times as high as the electrical power consumption of this unit is. And the same characteristic is also shown in the blue curve above, but with other units. Here we have on the y-axis the kilowatt hours of electricity consumed to compress 1 ton of steam. So for example, a compression with factor 3 requires about 100 kilowatt hours of electricity per ton. And on the right, this red diagram, or we call it a temperature operating map, you see which temperatures can be reached with a up to 3-stage compressor as function of the temperature on the source side. There you see that up to 250 degrees Celsius are possible when we have on the source side, say, about 150 degrees Celsius, meaning about 5 bar inlet pressure. Then we can even come up to 35-40 bar on the outlet side, which corresponds to the 250 degrees Celsius. The next slide, please. Now I would like to show some applications of realized steam compressor projects in the last few years. Here there is installation at a paper mill in Sweden, where 2 big 6-cylinder compressors are installed. They are double-stage compressors, compressing steam from 3.2 to 16 bar. The 16 bar are required to supply this paper pulp dryer with heat. And out of this paper pulp is coming out steam when the product is dried under a certain overpressure, under about 3.5 bar. This is contaminated, this steam what is coming here out. This has to go to a through a cleaning stage. Finally, a 3.2 bar clean steam is resulting from that. And this can be compressed now with our units to the 16 bar. And so this complete drying process is more or less self-supplying. The only energy input is here the electrical power demand of these two compressors. With this compression from 3 to 16 bar, it's about a factor 5 of compression ratio. We reach here a COP factor of about 4.2. Next slide, please. Here is also a 6-cylinder compressor as yes, installation drawing shown. It's installed at a chemical plant in Germany where steam is recycled. The steam on the source side is coming from a product cooling. It's available with 2.3 bar absolute. And a demand on this side is on a higher pressure level on 4.9 bar absolute. They have a steam distributing pipe which is supplying heat for different consumers. And here for this compression, a single stage compressor is sufficient. So all 6 cylinders are compressing here in the same way. And since the compression ratio is here also not so high, it's only about factor 2.2, 2.3, we get here a very good COP factor of about 9.5. Next slide, please. Here is also an installation at a chemical plant in the US. This is taken here in the presentation because it shall show that also on higher pressure levels this works. Here on the inlet side we have about 14 bar gauge, and on the outlet side 34 bar gauge. And since now we are with the inlet steam temperature and the outlet steam temperature on quite high temperature levels, we have to do the steam compression a little more carefully. So therefore, we need here 2 stages, although the compression ratio is only about 2 point something, so it's not that high compression ratio, but the steam always becomes hot while compression, and so since we even start at quite high temperature level, we have to do it in smaller steps. Here we reach a COP of about 7.7. Okay, next slide. Here another installation at a chemical plant in the United Kingdom, where steam is recycled from cooling of an exothermic reaction, available there on 5 bar absolute level. And this steam cannot be used at this plant on this quite low pressure level, but they have a demand or a steam distributing pipe again on about 20 bar absolute. And so the steam is compressed into this onto this pressure level. And here we have a compression ratio of about 4. And by this we reach here a COP factor of about 5.3. For the full available low pressure steam flow here of 16 tons, 2 units are necessary, 1 6-cylinder unit, which manages about 11 tons per hour, and a smaller 3-cylinder unit for about 5.5 tons per hour. Okay, next slide, please. Yes, last but not least, I would like to show our innovative spilling steam compressor, which is now developed in the frame of the EU funded SPIRIT program, what also Sonja has mentioned at the introduction. The idea of this unit is to have a smaller unit than we typically do. So it's a quite small 4-cylinder steam compressor, which is small enough to be put into a container. We have the idea to standardize these machines, that they are always 4-cylinder units. Also put all the piping, the wiring, the insulation and so all into this container so that it's easier to be planned for the customer, easier to be installed. So it shall become some kind of plug-and-play system for smaller thermal power loads, smaller steam flows. And it shall also become some kind of serial production also to get the costs down. And what we are installing here at Smurfit Kappa in the Czech Republic is here a compressor for compressing flash steam from a condensate expansion available on about 1 bar gauge, and it shall be compressed to 5 bar gauge so that it can be used directly again for the drying cylinders. This 4-cylinder unit manages about 1 ton per hour of steam flow, and with about 110 kilowatt electrical power consumption, finally a CRP of about 6.4 results. Well, this brings me to the end of my presentation. I'm looking forward to the further discussions with you. Thank you.
Thank you very much, Christoph, for presenting the spilling applications, also in combination with heat pumps. And I see that you've got so many questions in the chat waiting for you, so I think you really got our audience attention. And about the questions, I would just like to remind you to add the name of the speaker that you're addressing before asking the question so that there is no confusion. Thank you, everyone. So let's now move to our next speaker, John van Rooyen from GEA Heating and Refrigeration Technologies. John is Development Manager of Sustainable Energy Solutions at GEA, and for more than 30 years, he has been active in industrial refrigeration technology, and for more than 12 years, he's been involved in developing sustainable energy solutions, incorporating heat pump technologies, and thus contributing to the challenges related to climate change. So, John, the floor is yours. I see that your presentation has a very interesting title, Factory with Huge Dreams. So let's hear it.
Thank you, Sonia. Yeah, the title of my presentation is A Factory with Huge Dreams. Please forward the slide, Marina. Innocent was intending to extend their production facilities in 2016 to enlarge their production capacity, but their intention was not to add more impact on the environment. So their intention is it should be net zero also on the impact of the environment we are all living in. And it was decided in 2019 to build that site. Please continue. If you look at the typical food processing, to enlarge the shelf life of a product, is that a product is heated up and cooled down again. In this typical example, product is heating from 5 degrees to 95 for pasteurization, and then later on cooled down again to 5 degrees. So typically what you see in food processing is that the entering product temperature is the same as the leaving product temperature. Only topic is to extend the shelf life. Heat has to be added and taken out again. Please, next slide, Arena. If we look at the, yeah, okay. If we look at the initial design, you will see a Sankey diagram of the demands for this plant. You see the electrical demands and also a certain steam demand. Originally, the UK-based consultant intended to opt for a CHP plant, combined heating and power plant, to be more sustainable at that moment. But still, the solution was in burning fossil fuels, which was not the intention of Innocent at that moment. Next slide, please. If you look at the original setup, okay, you're quite quickly with the animations. Can you go one step back? Yeah, please, thank you. If we look at the demands for HVAC, air conditioning, offices and sanitary, there was a demand for 65 degrees water at about 1.5 megawatt. For the pasteurizers and CRP, there was a demand of 2.5 megawatt of heat at a temperature level of 95 degrees. And on steam level, there was a demand of 1.4 megawatt for aseptic filling of the bottles, but also 0.8 megawatt for melting the concentrated product for it. On the cooling side, there was a demand of about 7.5 megawatt at -3. Please forward the animation. So on the bottom, you see an ammonia plant which generates an amount of cold transported via glycol, and then the rejected heat is dissipated with air coolers or hybrid coolers to the ambient. On the top part, you see that a gas-fueled boiler was intended to install, creating the heat for the demands on 65, 90, and on steam requirement. To be more sustainable, and as indicated, the CHP plant was intended. So that plant would require 10 megawatts of heat, where the majority was required for heating, and also a certain amount was applied for electrical power for the refrigeration plant for it. Please forward the slide. Go back to the first slide, a factory with huge dreams. Initially, GEA was invited to quote for the processing part of the juices and the smoothies. But as GEA has, besides a food processing division, also has a heating and refrigeration division, both divisions sat together and came up with an idea. Please forward. And there, at that moment, we attracted Innocent to a new idea, which could be resulting in a carbon neutral and 100% new renewable electrical factory, which was their dream. Please forward. With GEA's sustainable or holistic approach on sustainable energy solutions, we don't focus only on process parts in itself, where you can reach out or gain efficiencies for it. We look at a total holistic view of the total process. There's the advantage that we can sit together with the process engineers and the utility engineers within one GEA at that moment. Please forward. And again, if we look at the heating of the product and cooling down again, first tier is to minimize the required amount of energy. What we did together also with Innocent and our colleagues of process engineering is lowering the pasteurizing temperature, making it possible to go for new solutions for it. We also, from GEA side, supported the company who provided the melters to step away from steam and do the melting of the product with hot water of 65 degrees. On the cooling side, we implemented a multi-temperature approach for cooling. So by applying different temperature levels, also your COP of the total solution is increasing. And we also applied state-of-the-art piston compressors to reach out the highest COP level for these kind of applications. Please forward. The second tier is reuse of energy, and there we focus on the pasteurizers that the majority of the heat required for heating and afterwards cooling is internally cascaded back. So reduced, the final result is a reduced demand of the top part heating and the low part cooling demand for it. Please forward. The next step is upcycle energy. As we all know that refrigeration plants reject the heat from the product or from different rooms, but was in the past dissipating all the heat to the ambient via the condensers. But here we also address the opportunities to Innocent of heat pumps already available on the market at that moment, and that we apply heat pumps for the energy upcycling to a certain temperature level for it. Please forward. And the last tier to go to net zero is harvest sustainable energy. And as Emerson decided to apply wind and solar, they would be able to create a completely fossil-free new plant for it. Please continue. As indicated by the holistical approach by the mutual teams of Innocent and Gaia. Please forward one animation. Yeah, we focused on an integrated cooling and heating solutions with heat pumps for the process part, HVAC, and e-boilers for the aseptic filling. What you see now on the bottom right part is that the melters are not anymore on steam. They have moved to the upper part of hot water 65 degrees, and we minimized the hot water temperature of 95 degrees to 90 degrees, being able at that moment to generate also that heat with heat pumps. Please forward one animation. So still we have a refrigeration plant on the low temperature side, but as you can see, we have only one condenser not dissipating that much heat anymore, and a large amount of the heat is now taken away by the heat pumps. So the heat pump of 65 degrees is generating 65 degrees water, and it's also the feeding of the 19 degrees heat pump. And to be able to generate still steam, an electrical steam generator was indicated. Please forward, Irene. And as you can see, initially the condenser heat was about 9 megawatt. Now we take away 4 megawatt, so almost half of it to be able to generate the heat. Still, there is an overload of heat from especially HVAC cooling, which has to be dissipated. Yeah, please forward one animation. And if we now look to the total solution as shown here, we need an electricity demand of about 4 megawatt, and we were able to bring down the fossil fuel demand from 10 megawatts to 0 megawatt. So that was also a huge step and a huge opportunity for Innocent. And I think that's also the reason why we were granted with this project. Please forward. As indicated, the solution starts with an in-depth process review, and also in this case, it's not only with the process engineers of the customer, but also with the process engineers within Gaia. We all have to learn from each other and challenge each other to come up with better solutions, which are more sustainable nowadays. Please forward one animation. So with that internal pre-discussions, we were able to define this final solution. On the lower left, you see still a glycol demand of -3. We have introduced a 10-degree water system for HVAC applications, and now with total 4+1 piston compressors, we are able to reject all the heat required. Part is still, if not used by the heat pumps, provided to the ambient, but as indicated, at least around 50% is now captured to generate 65 degrees water, 90 degrees water. Gaia also applied the other utilities like electrical steam boilers, but also potable water treatment, compressed air plant, and nitrogen generation. And there we also introduced a heat recovery from the air compressors to preheat all the water which is required on the total plant. Please forward. Now you see a renewed overview of the Sankey diagram. of all electrical demand, because there's still a steam demand, but that is driven now electrically, and the steam demand generated via fossil fuels has disappeared. Please forward. So at the end, together we were able to create for Innocent a carbon neutral and 100% new electrical renewable energy solution. Solar panels are already installed. Wind turbines are in preparation, and if they are installed, the majority of their electrical heat demand can be generated on site. And in certain periods, they have even an over amount which they can export. Until the wind turbines are not yet in operation, they apply green electricity from the grid. So at the end, in this way, we were able to create a blender which is net zero. Please go to the next. Yeah, Innocent, the blender, powered by nature and generated by Gaia heat pumps for it. It's already in operation since 2021, and despite there were some initial challenges, but all functioning well, and also it's quite appreciated by Innocent that Gaia came up with this solution, and we see also a spin-off in other industries with this kind of solutions for it. I think it was also requested by Benjamin, but also to show that this is an example of a solution which is already in operation, but Gaia developed also other solutions to contribute in general to the decarbonization of the industry. Please forward. Yeah. One of the other examples is, and you see it is also in the format of the Annex 85 sheet, that's the Gaia AddCool. It is a CO2 heat pump initially developed internally for spray drying processes, where we on one side generate chilled water for the milk preparation part, and we are now generating with this waste heat hot water of 130 degrees, being able to heat up the air for the dryer up to 120 degrees. And temperatures can range from, let's say, 50 degrees up to 130. One important aspect to mention is with CO2 as it runs supercritical, is that you should have a large delta T on your heat sink side. This will increase the COP gradually with it. Another example is also, please forward to Irene, is an example which is also in cooperation with other companies, earlier shown by Benjamin in this project. Over here, it's a project for a pet food factory in Norway, where we generate chilled water in 2 stages. We compress it up to 95 degrees. There we evaporate in a cascade heat exchanger water at about 90 degrees, so subatmospheric, and it will be compressed in a few stages with pillar centrifugal fans to a value of 120 degrees. And as what you all see in solutions where Gaia is incorporated, we focus on sustainable refrigerant to apply. So the natural refrigerants like ammonia, water, hydrocarbons, as indicated also in the Spirit project for it. But water also has a huge opportunity therefore. And this is what the end of my presentation. Thank you for your attention, and looking forward to the questions and opportunities to exchange more information about it.
You do indeed have some questions in the chat as well, John, so I will leave you to them.
Okay,
Thank you very much for the presentation. And indeed, the factory with the blender featuring the collaboration between Innocent Drinks and GEA was also submitted and at the 2021 edition of the Heat Pump Award and won the People's Choice Award. So I take this opportunity to ask you if you have some projects, interesting projects with heat pumps. Please feel free to apply to the Heat Pump Award, and just you can take a look at our website and you will find all the information there. Or you just can write it in the chat and we can get back to you with more information. Now let's move to our next speaker, Sander Gelen from Gelen Counterflow. He's being CEO at Gelen Counterflow since 1997. And he is going to present the Gelen Counterflow dryer. So please, Sander, the floor is yours.
Yes, good morning. Thank you, Sonia. This is a picture of our Gelen Counterflow electrical dryer. And for those people who don't know us, we have been building counterflow dryers and coolers since 1980. Application was initially 40 years ago, mostly for animal feed, for chicken and pigs and cows. But now, since the last 20 years or so, most of what we do is for drying and cooling of food for people, dogs, cats, feed for fish. And we started the development of our first electrical dryer around 10 years ago now, in 2013. And that was triggered by my visit to a specific coral reef in the Virgin Islands in 2010, which was exactly 20 years after my first visit to that same coral reef. And the coral reef was dead, as most of you probably know by now, that a lot of our coral reefs are dead. And that was because of our environmental problems and mostly because of our emissions of CO2. So I analyzed the situation and I basically concluded that I am part of this problem and therefore we should be thinking about how to move forward. And I decided that I want to become part of the solution rather than being part of the problem. So I came back from my trip. It was a long sailing trip, and together with our management, we decided we should be changing our strategy and to say that everything we do should become 100% sustainable. And of course, that starts with your office and your factory and whatever. But in the end, the big one is obviously the machines that you make. And particularly in our case, those dryers are very gas or energy intensive. So it took us a couple of years to build the first prototype of this electrical dryer. And luckily, we could then test that first prototype with one of our biggest customers, which is Royal Canin. That's part of the Mars Pet Care Group. And they themselves have a very ambitious sustainability strategy to phase out all carbon emissions before 2040. So we connected the prototype of our electrical dryer to an existing pet food dryer in Poland, and we ran it for roughly 6 months. And we needed not only to test the heat pumps, but also the heat exchangers, the control systems, etc., the integrated system. And the results were very good, so we started to scale up. Next slide, please, Irene. Yeah, so basically to show you a flow sheet of what we're doing. In this flow sheet, you see on the right-hand side the dryer and the cooler with a vertical black line through it indicating the product flow. I will not go into all the details of how our dryer works in detail, but essentially there is product coming in on top of the dryer, falling through the different cascade decks and coming out at the bottom, then going to a cooler, and then back to packaging or storage or transport or whatever. So that's the black line. Now the red line, which you see coming out of the top of the dryer, is the air, which is the spent air, the wasted energy in there. And normally we would exhaust that to ambient, and that's what we've been doing for a very long time. The blue lines are water, but I will go into that in a second. But the red lines, you first see one top line, red line going out on the top left corner being exhausted, and that's the way we used to do it before. And then at the bottom you see that the cooler red line is coming back into the dryer. And we've been doing that for a long time, reusing the cooling air, which contains a lot of energy, of course, and reusing that up in the dryer. But the blue lines are relatively new in our electrical dryer. And on the left-hand side, what you see is what we call a counterflow recovery unit. So we first start by condensing that air which comes out of the dryer, because it contains all the latent heat from the evaporation of water out of the product. And what we want to do is to condense that air as quickly as possible in a relatively short time frame, so we recover very efficiently the latent heat. And we can recover in that particular location between 65 and 75% of the energy which is contained in the top of the dryer. However, it comes out at a relatively low temperature. So there is 40 degrees Celsius, roughly, water coming out of that energy recovery unit. And then you see that blue line moving back into the dryer and ending up in two different heat pumps. So in the middle of the blue lines, you see two heat pumps. And why did we do it in two heat pumps? Because each part of the dryer has its own temperature profile. So we wanted to make sure that we run the heat pump at the correct temperature for that part of the dryer, and that way optimize the COP. So that's how we basically design the flow. Now, if we go to the next slide, please, then you will see an animation of how that system looks like. In this example, in a 6-stack dryer, and we're running around the dryer now, and you see at the back the two heat pumps in the flow diagram, the two buffer tanks that we're looking at right now. And then in a minute, when we go to the not to the next slide, I'm sorry, Irene, we just wait for this animation to move on. Then you will see in a minute how the energy is passing through the dryer. You see here the decks where product is contained, and air is flowing through each of those decks, typically the hot air. And that used to come from gas burners or steam heat exchangers. Basically, that part of the system is not different. But now you see the air coming out of the dryer and then first passing through a cyclone to take out the fines. And then the clean air is moving into what we call the counterflow recovery unit. And after that, when it's cooled down, it is going into another hydrocyclone before the air is actually exhausted. So the air itself is going out, but we've taken out the energy from that air in the counterflow recovery unit. So in this part of the animation, you see a simulation of what happens in that counterflow recovery unit. There is plate heat exchangers in there, and we call it the counterflow recovery unit because the air is moving top down, and the cold water, the relatively cold water coming from the heat pump, is moving in the opposite direction. So we're using the cold side of the heat pump to trigger the condensation, which allows us to recover the latent energy. And then the heat, which is in this case simulated in the green flow, is moving to two heat pumps and then being boosted to two different temperature levels. And those temperature levels are then moving into the dryer, where we have what we call a secondary heat exchanger, because this is where the dryer now picks up the heat from the heat pumps and converts that into hot air. And again, we do that with plate heat exchangers to minimize the pollution and to make the pollution or to clean up the pollution as easily as possible. Next slide, please. So an essential part of that is also recovery. Heat pumps is obviously necessary, but in every process, you also need to figure out how you're going to recover energy from that industrial application. And we've done it through this recovery unit, which, like I said before, is vertical and consisting of a lot of plate heat exchangers. Next slide, please. So a couple of references. The first one, which we installed, is in South Korea. It's 1.2 megawatt thermal, been operational since May 2022. Currently already in an upgrade to a new type of compressor, which can even give us an even higher temperature than before. Next slide, please. And another reference already running is in Norway, in Bergneset with Cargill EWOS. They are drying extruded aquafeed, 3.3 megawatt thermal, been operational for over a year, and the COP is over 4, roughly 4 in practice. What we're going to look at next is a little video, but before we switch there, maybe I should mention that we have 2 more electric dryers already underway. One is waiting for startup in China, and one is being installed in Thailand at this moment. And there is 4 more electric dryers that we expect to get the PO for this year, which we will be installing next year. And then next, what I'm going to show you is a 2-minute video from Cargill EWOS in Norway, showing you exactly the details of that electric dryer. Irene, please start the next slide.
I Arktis, i midnattssola og nordlysets rike, der majestetiske fjell møter isklart hav, ligger Cargills nordligste fôrfabrikk. Her produseres sunt og næringsrikt fiskefôr til kunder i store deler av Nord-Norge.
I havbruk står fôrproduksjonen for mellom 75 og 90% av CO2-utslippene. Det er derfor avgjørende at vi i næringen tar grep for å bedre bærekraften.
80 millioner kroner er brukt til å bytte ut gass med strøm som energikilde i produksjon. Resultatet er verdens største vertikale fôrtørkemaskin på hele 15 etasjer og 4 elektriske varmepumper som gjenvinner varmen fra tørkinga.
CO2-utslippene reduseres med 3000 tonn CO2-ekvivalenter per år. Det tilsvarer utslipp fra 2350 biler.
Energiforbruket til produksjonslinja er redusert med hele 75%. For fabrikken som helhet er energiforbruket kuttet med 15 millioner kilowattimer, som tilsvarer 20%. I dag er Cargills fabrikk på Bergneset en av de mest energieffektive produsentene av fiskefôr i verden, og godt på vei til å bli verdens første fiskefôrfabrikk uten lokale CO2-utslipp. Et pionerprosjekt for fremtidige utslippsfrie anlegg. Cargill skaper bedre resultater for fisken, for havbruken, for miljøet og til syvende og sist for forbrukeren.
Okay, Irene, next slide, please. Okay, this one we've already covered, but actually there was just a question in the chat about the counterflow heat exchangers. How do we handle the fouling? And actually one of the reasons why we designed it this way is that the condensation is helping us to clean up the plates. So the condensation is going to be triggered in the top 20 centimeters of this heat exchanger. And there's going to be a lot of water, thousands of liters of water per hour is going to be flowing down those plates and therefore pulling with it any fines or buildup. So they're actually staying surprisingly clean. We had expected that once a month the clean would be necessary, but in practice that frequency is significantly lower and in some instances less than once a year. Okay, next slide, please. So now I have a couple of pictures of that installation. This is where you see 2 of those counterflow recovery units side by side. Next slide, please. And that's the top where you see the water moving in and out of that heat exchanger. Next slide, please. This is where we have installed 4 heat pumps. So it's in a separate building next to the dryer. And maybe some details about the heat pumps that were requested also in the chat. These are Combitherm heat pumps from Germany using Bitzer screw compressors. We are using refrigerant R1233ZDE. We have a source temperature flowing into the heat pumps of approximately 40 degrees Celsius, a little higher sometimes. And the sink in Norway is roughly 100 degrees max, but in Korea we are already at the sink of 120 and now upgrading to 130. So this already tells you that we are in the middle of this iteration process where you need to get into as soon as possible. Iteration, continuous improvement. The whole system is working, but you can improve efficiency, you can higher the capacities, etc. So that's what we're doing now continuously together with the Combiterm, Bitzer, and also with our customers, Royal Canin and Combiterm and Cargill. Next picture, please. That's the backside of the heat pumps. And then on the next slide, we will see what we call the secondary heat exchangers. This is where the hot water and is moving into the dryer and going to pass its heat onto the air that we're going to use for drying. Okay, next slide, please, Irene. And maybe if you could fast forward 5, 6, 7 times so that I have all the text on the screen. Yeah, that's the last one, correct. I'm not going to go through each of those bullets in detail. I just want to show you what are some of the financial aspects of these dryers. Now, first of all, you need to know that drying is in the world that we are in is typically more than 50% of the total energy consumption of an extrusion line. This is maybe not necessarily true for every type of food factory, but for extruded products, drying is the big one. That's where the biggest energy consumption is. And then the gas and the steam is typically 90% of the total cost of ownership of a dryer. So depreciation and other costs like maintenance are relatively small. The big factor which determines total cost of ownership of a dryer during its 20 or 30-year lifetime is the energy consumption, and up to now that was gas and steam. Now, the capex for an electrical dryer is significantly higher than for a gas or steam dryer. As you can probably imagine from the slides that I showed you before, there's a lot of complexity involved. It's not only the heat pumps, but it's also the heat exchangers, it is the control systems, it's the piping, etc. So the capex side is significantly more expensive, up to 2 to 3 times higher than for a standard gas or steam dryer. But first of all, you can reduce your gas and steam consumption by 100%, so you don't need gas or steam anymore. You reduce energy consumption by, in this example, 75%, so the COP of 4. And so the remaining 25% energy consumption is obviously electricity, which can be or should be sustainable. And then what is the price of electricity? Well, of course, that depends on a lot of things. In Norway, in this example, we are very lucky, and our customer is very lucky to have a situation where electricity and gas are priced almost the same per kilowatt hour. And that is quite different in countries like Germany or the Netherlands, where there is easily a factor 3 or more between those two. But in a place like Norway, it means that 75% energy consumption means 75% energy cost consumption. And so you can imagine that the payback in that example is pretty fast. In other countries, we have maybe not yet reached that, but with the CO2 pricing that's coming up, or already existing in some industries, of course, the payback time is brought down quite significantly. Next slide, please. Yeah, maybe again, give me 4. Yeah, that's it. So what we've done already since about 4 or 5 years is that all our dryers are prepared for heat pump upgrades. So even people who are not yet there, who are not yet willing to take the risk of going for the heat pump, or because their energy pricing is not ideal, we are installing dryers there which can be upgraded with heat pumps relatively straightforwardly. We also make it possible for them to do a step-by-step electrification. So in the example that I showed you before, where there is 2 heat pumps, you could actually start with only 1 heat pump in the lower temperature zone, which has the highest COP, and therefore do a recovery of energy and money on the low temperatures first, and then add heat pumps step by step on the way. So that makes it financially more attractive to do a phase out in steps. We're still building in redundancy for electric dryers. So we are commissioning them with gas burners as a fallback. And also you could optionally avoid peak electricity prices. So in some countries where there is a huge spread in peak and off-peak electricity prices, economically speaking, it is interesting in the short term to optimize and to switch from gas to electricity, and therefore maybe reduce the amount of gas savings that you are. So you're not completely going for the full gas savings, but at least economically you can make it more attractive. And finally, boosting electric coils or gas burners can be used to boost temperatures to higher levels than those that are available from our current generation of heat pumps. So the heat pumps we are using now are somewhere in the 120-130 C range, and some of our processes require 140-150. So you can then add additional temperature to the air by boosting it with either electric coils or gas burners. Next slide, please. And of course, there is some conditions, and I'm not sure whether it's been mentioned before, but the big question we get obviously is what is the availability of electrical grid capacity? And in some countries, it's no problem. In some countries, it is fixed in relatively short term, and in other countries, it's a lot harder. So this is one of the main bottlenecks that we're running into now, is how fast can our customers electrify depends on the availability of grid capacity. And obviously, you need space in the plant or next to the plant for the additional heat exchangers and heat pumps. That was my presentation, Sonja. Thank you.
Thank you very much, Sander. I see that there are a lot of questions for you in the chat as well. So let's go on to our next speakers. So far, we've heard the voice of the technology providers, but let's now hear something about the experience of the end users. So we have here Vincent Grass. Vincent Grass is Nestlé's corporate functional leader for refrigeration, which also includes heat generation via heat pumps. He defines the corporate strategy and standards for the choice of refrigerants, and he is involved in implementing natural refrigerants projects in Nestlé across the globe, as well as mitigating their associated risk. Prior to joining Nestlé 13 years ago, Vincent spent 2 years at Johnson Control and 10 years at Equans. So as my colleague Irene, helping us in the backstage, would say, Vincent, is your time to shine.
Thank you, Sonja. Can you move the slide, Irene? Well, hello everyone. So today I'm going to present shortly what we do basically in terms of heat pump integration to decarbonize our food industry. Next slide, please. So maybe just an overview of Nestlé in 2022. So Nestlé is currently the largest food and beverage company in the world. We are existing since more than 155 years. We do operate or sell in 188 countries. We do operate 344 factories, and we sell 1 billion of product every day. Next slide, please. In terms of sustainability, here is our roadmap. So we take an approach basically to look across the full value chain. So our carbon footprint has been estimated in 2018 and is, as you see on the bottom right, the largest part of it is actually related to our ingredients, so mostly to the agriculture part, so which is more than 55% of our emissions. And then if you look at the manufacturing or even logistic, each of them is roughly between 5-7% of the total carbon emissions we have. So our aim is to reduce our emissions by 2025 by 20% and to be to have our electricity fully renewable by 2025. Then to reduce our emissions across the full value chain by 50% in 2030, and then latest 2050 to reach the net zero. Next slide, please. So to address this decarbonization journey, and the most difficult part, as I mentioned, because in 2025, we should be there with our electricity being fully renewable. then the biggest challenge in manufacturing is about decarbonising the thermal energy. And here, basically, there are two approaches we see out there, or we could also use. Is on one side, you can simply take the quick and dirty approach, which is replace the way you generate steam, the way you generate hot water, by changing the generator, going, for instance, for a biomass boiler or another solution. But this will not deliver necessarily, the efficiency gain, will not be a well-integrated solution. So our path, the one we decided to follow, is actually to go through the reduce, rethink, and replace sequence, which delivers an optimized utility network, the synchronized integration of heat source and heat sinks. And obviously, this whole system needs to be managed properly with a digital energy management system. So that's the key, basically, deliverables we also need to have when we do implement this reduce, rethink, replace strategy. Next slide, please. So following this more complex path leads to a reconfiguration of the manufacturing facilities. And this means typically integrating more renewable heat sources, for instance, renewable energies, solar, wind, but also use of sustainable biomass. In this case, for instance, we have coffee as one of our products. And we have spent coffee grounds available. Obviously, we take advantage of that and reuse this waste to actually generate heat. Electrify with heat pumps, that's a key technology for us, which is playing an important role in improving the efficiency. And then, as it was also shared earlier by Sander, basically developing disruptive technologies, integrating basically process equipment, that need lower temperature, that are quite disruptive, like the vertical dryer from Guillain, for instance. But there are many other products or processes that needs basically to be to go through a rethink process. This is also part of the journey. Then obviously the rollout of mature technologies and the elimination of steam wherever possible is also part of the journey. So if we do basically a good integration here, it's more than actually addressing the greenhouse gases emissions. Obviously here the aim is to have 100% reduction. But basically here with one stone, we hit multiple targets. We also improve the efficiency. And what we see as we develop our roadmaps is a reduction basically of the kilojoule per tons up to 70% if we do a proper heat integration. And obviously also a water usage reduction because we pump the heat around, we don't evaporate any water through cooling towers. So it generates also significant water savings. And altogether, it brings us, let's say, to the next level. It builds more resilience in our business. And it's also very important for all the infrastructure around the factory is that the efficiency or the community even is that the efficiency is being improved, and therefore, let's say, the energy we use is significantly reduced. Next slide, please. So there are many opportunities in food in the food industry to get boiler free. We have many examples where we actually could integrate heat pumps to combine heating and cooling. You see here on the picture, for instance, on the left side, all the thermal networks we have in a given plant and their users. And on the bottom side, well, traditionally, let's say, first those users were running with a chiller and a boiler. So two separate systems, a silo approach. But with the integrated and combined heating and cooling solution, we actually managed to electrify everything and pump the heat around instead of rejecting it and dumping it into the atmosphere. So that's quite something we do more and more, and we do have in our own roadmaps, for instance, in Europe, in almost every sustainability roadmap we have in our factories, a heat pump in scope as a milestone in our decarbonisation journey. Next slide, please. So what are the heat pumps we use or plan to use? So I will give a quick overview here. So the heat pumps we use at unit level, that means at machine level, which is decentralized. If we think about a full factory, are typically mechanical vapor recompression system. So if you want steam compressors or blowers, we have more than 35 systems installed worldwide that are actually lifting temperature steam from 70 degrees up to 130 degrees. So this is something we have a standard we roll out and little by little convert all our units. Next slide, please. Then when it comes to a process line, which is more than one single machine, a more end-to-end approach for a process system here, we do see opportunities, obviously, for water cycles. Again, mechanical vapor compression system, also like the steam compressor that was mentioned by Spilling earlier today. But we also do see potential in a partially decentralized way, or even decentralized way for CO2 high temperature heat pumps. Like it was presented by GA. For instance, we do see opportunities here and we look for it basically to heat up air from ambient temperature up to 120, 130 degrees. This can be used in makeup air for dryers. It can be used for desiccant wheel regeneration on the humidification units. There are many potential usage, and CO2 is a good choice for water or air requiring a high temperature lift. Next slide, please. And then at plant level, well, this is actually where most of the action happens. This is actually looking then at the factory level, and this is where we have the biggest opportunities, to centralize and benefit from all the synergies we have. Quite often, the boiler house is next or to the chillers, and we can do a lot with heat pumps. So we have been using ammonia heat pumps since many years. I just gave here an example of a factory in Halifax in UK that has a heat pump installed since 2011, an ammonia heat pump that generates the hot water and actually replaced a coal boiler. So that was actually a good move. So we do deploy these solutions, like I mentioned, as part of our sustainability journey. Now they are identified almost in each and every factory. And then for factories that do have an above a steam demand, say for sterilization or even higher temperature, here we do see basically two options. Is basically to work with a steam generating heat pump using hydrocarbon as a refrigerant, so pentane if it's to go up to 150 degree, 145, 150 degree, or a cascade system, as it was also mentioned earlier, between a hydrocarbon and then a water cycle, so a steam compressor, so make the water boil and then compress it to reach the temperature you need. So that's the direction we are currently taking with regards to heat pump. As you can see, all those heat pumps use a natural refrigerant, so either ammonia, CO2, water, or some hydrocarbons. They are all ultra low GWP, so don't have a high global warming potential. And very important, they don't decompose into forever chemicals that accumulate in environment. So that's having said that, can you move to the next slide? So the summary here, if we look at our manufacturing plants, like I said, well, we do have some opportunities at unit level. Some application may have, some opportunities because we have a good simultaneity of the heat sinks and cold sinks. So we can actually integrate locally and decentralize a heat pump there. But what we see currently is mostly the use of mechanical vapor or compression. Obviously, at process line, more synergies and some opportunities for specific demand profiles. Like I said, high temperature lifts that is not going to be well covered by a centralized system. So CO2, for instance, is going to be a better choice. And then at plant level, well, this is where we have the maximized synergies and the potential for combination with multiple other heat sources, not only heat pumps, but this can be heat recovery, solar thermal. So basically to build an energy network, so hot water networks, basically that can actually take the heat, from multiple sources. Next slide, please. So what we need for the next steps? Currently, as I mentioned, we do have our roadmaps in our plans. We do have identified all the steps or most of the steps to actually reduce significantly our emissions, meet our targets. So what we see and what we are doing currently is working on the integration of hot water heat pumps, so not necessarily yet the very high temperature, although we would like to make our own experience with that. And the very high temperature are also identified, so the steam generating heat pumps are identified and needed, as well as the CO2 heat pumps for air heating. And we will need it according to our plans in 2026, 2027. The demand will be there and will be higher. Currently, we would like basically to integrate and to pilot some of these projects to make our own experience with those systems. So you see on the bottom here a little chart. It's not very detailed, but showing basically which are the type of refrigerants and temperature levels, let's say, we consider for each and every refrigerant, as well as a rough idea about the capacity we are looking for. Next slide, please. That's the last one. Thank you.
Thank you very much, Vincent. And I see that you also have some questions in the chat. Maybe since you're here, you can already answer one live, because we're going to our Q&A session. So for you, Vincent, Frederick Bless asks, hello, Vincent, as Nestlé is present internationally, are you starting everywhere at the same time, or are you starting with some specific plants in order to learn from them and copy that work?
Well, yes. We are divided also in multiple product categories, so we do have different needs depending whether we do infant formula or water, right? But bottled water, it's not the same energy demand and energy networks. So yes, we try multiple things. In Europe, this is really the leading continent currently on when we look at what's going on basically and what's happening also in terms of development of new technologies. So, but for instance, I can share in US we do integrate also ammonia heat pumps in a new plant. So we build there to actually cover all the hot water needs. And this is the same. We currently have projects for heat pumps in many different places across the globe. Just the latest one that come to my mind is actually in Vietnam, where we look actually in a combination between a heat pump and solar thermal.
Thank you very much. I think you can take the other questions in the chat, whereas we move to our first speaker, that was Christoph Fleischmann. Christoph, you presented the spilling piston steam compressor. I would like to ask you, what are the typical fields of application of this technology?
Yes, the typical customers so far have been chemical plants, like some references has shown, but also the paper and pulp industry we see here as a potential customer for the future. Also, we see here much more potential in the paper industry coming up. And with a small unit, what we are now developing together with a Spirit project, there we see new potential also for the food industry, for smaller, say, heat consumers, not in the big megawatt range, but maybe between 500 and 1000 kilowatt in that range. We see here a big potential also for pharmaceutical plants, food industry, maybe also in the paper industry to recycle, for example, heat from flash steam condensing or condensate expansion and the flash steam coming out of that, like it's done at Smurfit Kappa in the Czech Republic.
Thank you very much. And since I have you here, can I also ask you, how much does the steam compressor, the spilling steam compressor, costs? Because also economic, financial aspects are important.
Yes, the big units, well, it depends finally more or less to the number of cylinders what we are installing. The one cylinder units, they start at around 500,000 euros, and big 6 cylinders are then more in the range of 1.5 million. So these are quite high costs, and you also have to take into account that there are also surrounding costs which have to be taken into account, like piping, wiring, maybe a room, what is necessary. So you easily have costs of 1 to 2 million euros with such a project. But on the other hand, you can save a lot of energy. And with also the funding programs which are now available in many European countries, I think it's a very good time to do the investment now, and also with the perspective of upcoming CO2 prices. And so I think it's really now the time to do these investments.
Yes, completely agree. We need to decarbonize the industry in some way. So if it costs a bit more in the short term, in the long term, we will see the results. And to our second panelist goes my other question to John. Can you hear us?
Yeah.
Yeah, awesome. So John, on a more general note, what do sustainable energy solutions mean to you and to GEA?
Sustainable in this case refers to different aspects. And one of the first aspects is that sustainable should also be a cost-effective business solution. For new developments, yes, subsidies can help out, or grants, but at the end, each solution has to earn itself back, and mostly in these cases by energy cost savings. So yes, they must be cost effective, else they won't last for decades, and we will not reach the decarbonisation as required. Secondly, refers to the impact of mankind we have on the activities on our environment, the world we are living in. We have to reduce, or even better, reverse the effect of the climate change by stopping burning fossil fuels for heating activities up to 200 degrees. It's, as to say, really insane to burn fossil fuels up to a temperature level of 800 degrees to achieve temperatures of 200 degrees. And I think in all presentations, it was also presented that until that temperature level, solutions are available with more sustainable solutions for it. And also sustainable refers, as Vincent perfectly indicated also, that we as GEA would only like to apply natural refrigerants, and we want to stay away from forever lasting chemicals as indicated, because we shouldn't create another problem for within a few decades. So therefore, I think what Vincent indicated completely also answers to the vision what Gaia is intending for.
Thank you very much, John. And since you mentioned natural refrigerants, I do have a question for Vincent on that. So Vincent, you said that you're looking for solutions that are all using natural refrigerants, although some are toxic or flammable. So what is your message to the other end users perceiving this risk as unacceptable?
Well, I think as in all the end users basically have to manage process safety risk. Should it be on a boiler that also has flammable, they may have like kilometers of flammable gas on the roof, so I mean this risk can be managed. We are used in this industry to manage many process safety risks, including flammability. And we know how to do it. We know how to handle it, and we have good safety track records on that. So, I mean, this is mostly a perception that flammable is bad. Well, we would all love, let's say, to have a refrigerant that is not flammable, that doesn't harm the environment, and doesn't accumulate in the environment neither. But this is not yet available. Well, water is, but that only works, let's say, in a given in a given range. So there is no. It's all about perception. There is no. It's something the industry can manage.
Thank you very much, Vincent. And I do have a question for Sander as well. So Sander, in your presentation, you mentioned the role of the Garland counterflow electrical dryer in decarbonizing the food industry. And I also saw that there were some questions on this in the chat. But my question is, to what extent is, according to you, the food industry currently planning to electrify industrial heat demand?
Well, I think probably the food industry is ahead of most other industries. They are, first of all, big energy users, but also they are very often producers of consumer goods. And therefore, the combination of the financial side and the, let's say, the PR side of switching to renewable heat is very interesting. So we find that many of our customers are moving very fast and have been ambitious already for 10 years and also helping us to develop this technology. So I'm optimistic that the food industry is moving on average probably faster than most other industries.
I'm not sure if you can hear me.
No, we lost you for a second.
Can you hear me? Okay, now I'm back. Awesome. Thank you. Thank you for your answer. And to John again. John, to which temperature levels you see opportunities for decarbonization of the industry made possible with heat pumps?
Yeah, actually, this answer is already given by one of the slides of Vincent. I think he was aware of this kind of questions. And in short, up to temperatures of 95 degrees, ammonia is the best solution for it. For temperatures higher than that, with large delta T's, CO2 on the hot side, CO2 is a perfect solution. For higher temperatures, let's say to 150 degrees, as also in the slide is visible, hydrocarbons can be applied. Also as a feed for MPR, mechanical vapor recompression solutions. And yes, between 120 and 200 degrees, water vapor is the option where I think the demand is high for on the food industry. And that's also due to the fact that most of the plants have an infrastructure for steam. So there they can probably can be a little bit less energy efficient solution to go to higher temperatures, but you will save the cost of the infrastructure. So at the end, it's also a balance of the business case for it.
Thank you very much. Vincent, I've got one last question for you. So from an end user perspective, what is, in your opinion, the biggest challenge to face to make a successful heat pump integration?
Well, it requires, to be honest, a huge effort to make a successful integration. You need to bring together everyone, the process, the energy specialist. You need to understand very well how you operate the factory to be able to deliver a solution that actually covers all operating modes you have. This may be startup. Many modes are existing out there, and you may go for a heat pump, and then suddenly you realize, you don't have a heat source, so there is no heat available. So the effort up front, the engineering effort up front, the understanding of the process is actually paramount here to make it successful.
Thank you very much indeed. A lot of pieces moving. And Sander, last question for you. What is the business case for heat pump dryers?
Well, I think with dryers, to some extent, we're kind of lucky that they're really a very attractive piece of kit to electrify. As you saw from my slides and my diagrams, you can add the heat pump to the dryer itself and make a very compact and fast response system. So although I can see the point for a plant to centralize all of that heat recovery and heat redistribution through heat pumps, if you look at the separate dryer, which is using probably 50 or 60% of a particular production line energy, then it's very attractive to put that heat pump next to the dryer itself. Minimize piping, optimize efficiency, quick response, etc. So I think probably dryers would be one of the first pieces of kit that everyone should be looking at for electrification, because they will probably have the lowest payback time.
Thank you very much. And this was the last of my questions. I hope that all attendees got their answers there in the chat. I see that our speakers were very good at providing the answers. And I think that we can also close this webinar since it's 3 minutes to 12. So I would like to remind you all to follow Spirit. If you can go to the next slide, Irene. So yeah, here if you scan the QR code, you can follow the Spirit project under which this webinar was held. And also follow EHPA if you want to learn more about our activities, our upcoming events. I would like to thank every speaker that joined, every attendee that joined, and I hope it was an insightful opportunity where you could learn more about the world of high-temperature heat pumps and especially their concrete applications in the industry. I see a lot of applauses, so congratulations to all the speakers, and I will see you in the next EHPA event. Thank you very much. Have a good lunch and a pleasant day. Bye-bye.